Good evening, everyone. Welcome back to Theory of Computation. This is another prerequisite video, quite a short one though, on strings and languages. Okay, so this is a concept that's, to be honest, myself, I wasn't 100% familiar with, so this is slightly new to me going into the course. But it's fairly simple once you sort of see it and understand it, and it's not very you don't need to know lots about this stuff going into it. So doesn't make for a very dense prerequisite in terms of content that you need to know. After this, pretty much all we have is Boolean logic and then some stuff on proofs, and then that's pretty much it for the prerequisites. So almost there. But without further ado, let's not waste any time. Let's get straight into this. Okay, so before we talk about strings and languages, we need to actually talk about an alphabet. So I haven't put that in the title, but it's an important concept as well. So an alphabet, pretty much all it is well, mathematically all it is, right, is just effectively a non-empty finite set, basically. So an alphabet is sort of defined to be any non-empty finite set. Okay, so as an example, some sort of alphabet that you might see is we typically denote alphabets, so the sigma symbol here. So sigma 1 could be an alphabet, and it's basically just a set, and it could be maybe a set containing the elements 0 and 1. So that's an example of an alphabet, right? And I probably should have said this beforehand, but we typically use Greek letters to designate alphabets. It's basically just names of our sets, right? It doesn't really matter what we use if you're being if you want to be honest with yourself, it doesn't really matter what symbol we use to sort of name our set. But in practice, for alphabet specifically, we typically use Greek letters. So we typically use sort of specific capital Greek letters, right? It's capital sigma. If you know anything about Greek, capital Greek letters. We typically use capital Greek letters, and specifically, actually, we use sort of the capital sigma, so like this, and sort of the capital gamma, like this, effectively, probably should put that like this, to designate alphabets, right? So if we want to sort of name the set, which is basically our alphabet, because an alphabet is just a non-empty finite set, then we typically use capital Greek letters to do so. So and the capital Greek letters that we typically use are sigma and gamma. Those are just sort of choices that we sort of make. Okay, yeah, and so although we've seen an example of an alphabet which is just containing the elements 0 and 1. Obviously, the alphabet that you probably thought of when I said alphabet is also actually an alphabet in the mathematical sense as well, right? Because it's just basically I could define a set called a sigma 2, a sigma subscript 2, which is effectively just the set of all letters, right, in the English alphabet, right? And so effectively this itself is actually also a valid alphabet because it's just a set, a non-empty finite set, right? There's an end to the set, so there's some finite number of elements. I can count all the elements in my set, and it and it's not empty. It's not the empty set, right? So it counts as an alphabet, right? And to be fair, there's so many things count as an alphabet because there's so many non-empty finite sets, but it's just kind of funny that the actual English alphabet also counts as an alphabet. Pretty much any alphabet out there probably would also count as an alphabet, as long as you can store sort of the symbols of that alphabet within a set. Then it's an alphabet in the mathematical sense as well. So those two things are effectively an alphabet, like in the sense that you would think of, is also technically an alphabet mathematically. So I guess that's nice. So yeah, I mean, both these examples here that I've drawn, they're both examples of alphabets, right? So they're both examples of alphabets. Both examples. Sorry, just realized I'm of alphabets. Right. And so now that we know what an alphabet is, we're in a good place to define a string. Okay. So a string over an alphabet. Right. So a string over an alphabet is effectively a sequence of symbols. Actually, to be fair, I didn't even mention this, actually. I probably should have mentioned this. So the members of an alphabet are said to effectively be the symbols of that alphabet. Right, so for example, the letter A is a symbol of this alphabet here, sigma subscript 2, right? Because it's just it's an element within the set, within the alphabet itself, just an element of that set. And so we say that it's effectively a symbol of the alphabet, right? Because it's an element of the set which defines the alphabet in that specific case, right? That's just some sort of detail, basically just notation, right? Like just formalisms that we use to talk about the elements that make up our alphabet. We call them symbols, and so that follows on nicely. What follows on nicely as a string. Which is effectively just a sequence of symbols from your alphabet, which are typically written next to each other, but without commas, basically. So we say that a string over an alphabet is a sequence of symbols, specifically a finite sequence of symbols. I should probably specify a finite sequence of symbols from that alphabet. Usually written next to each other and without, basically not separated by commas. So basically, basically, you could always, it almost is like in a physical sense, if you like imagine like a physical string, kind of is just like that, and then like all the symbols are attached to each other one after the other kind of thing. Like if you were to attach all the symbols on a string and then connect the string between each sort of two symbols that are like adjacent, then you would effectively form a word, right? It's like every English word is a string, right? Because it's basically just symbols from the alphabet, like the English alphabet, right? You take symbols from the English alphabet and you kind of string them together, right, to make the word. Basically, that's kind of where it comes from in a sense, but just from definition as well. Effectively, a sequence of symbols. You can just imagine that as effectively just you're taking some symbols, right? Let's say I wanted to write the word abracadabra, and you're writing them next to each other. And typically with sequences, right, we have these commas between elements. So you might have like abracadabra or something, right? And obviously this is like a sequence, and maybe you'd write sort of these brackets here as well, but we don't need to worry too much about that. We remove those for the case of strings, even though typically with many sequences you might see brackets like this here as well. But in the case of strings, we don't have those brackets there. And then you would imagine that there typically be commas separating those things for sequences, but we also remove those for the sake of string. Basically, there's nothing connecting, well, there's nothing necessarily between the two adjacent symbols. So you remove these commas, and now I have a string, right? So I basically just have a bunch of symbols written next to each other and not separated by commas. So this is a valid string, right? And specifically, it's a string over the alphabet. I think we defined it to be sigma subscript 2, right? So, yeah. So, as an example, we have that abracadabra is a string over the alphabet sigma subscript 2, right? Because effectively, all of the symbols that we're using are contained within that alphabet, and we're just bunching some arbitrary number of symbols together to make the word abracadabra, and we're removing the commas, because technically a sequence, right, of symbols next to each other. You remove the commas, you remove the brackets, and this is what you make, effectively, right? This word. So, yeah, hopefully that makes sense. And another example, obviously, we defined sigma 1 to be the second containing the elements 0 and 1. So the symbols of this alphabet are simply just 0 and 1. But we can sort of use those symbols as much as we'd like to make a string, basically. So also 0, 1, 0, 0, 1 is also a string over the alphabet sigma 1. Right? Because I'm basically just, again, I'm using all of the symbols here are contained within that set, basically. And I'm just bunching them together in some sequence, removing commas. And I get that. Basically, that's what I get when I just arbitrarily choose a bunch of symbols from that set, put them next to each other, or put them in a sequence, and then remove the brackets, remove the commas. That's the outcome. That's what I get, right? Okay, so hopefully that makes sense. It's pretty sort of intuitive, I guess, right? Because effectively you're talking about words. So abracadabra is just a word, but it's also a string in a mathematical sense, and it kind of makes sense when you sort of put two and two together. Like this is how we can sort of mathematically talk about like words and things like that, right? Because effectively they are just strings from alphabets, which are just sets, right? So pretty much everything comes back to set theory, right? Okay. So the next thing I want to talk about is if I have a string, we'll call it W, but effectively it's just a bunch of symbols, doesn't matter how many, next to each other without commas. So if W is a string over some alphabet, is a string over some alphabet which I'll denote with sigma. So it's not any of the alphabets we looked at so far, just some arbitrary alphabet. Then we'll say the length of W, written, effectively we have this sort of modulus symbol. I'm not sure if you've seen that before, but there's two vertical lines sort of sandwiching a W inside. We call it a modulus of W. So effectively the length of W written sort of with the modulus symbol, modulus of W, or the absolute value, whichever one you prefer, is effectively all the length of the string is the number of symbols that it contains. Symbols, and I'll make this a bit, see if I can enlarge this a bit, this box, if it's going to let me, but it's looking like it's not going to let me. Hold on. Why is it creating an arrow? Hold on. Yeah, there we go. So something like this is the number of symbols effectively that it contains. Right? So effectively the length of some arbitrary string, which we denote with this absolute value symbol, is just the number of symbols that it contains. So the length of 0, 1, 0, 0, 1 is just 5. So if I denote that as a string w, then the modulus of w, right, with those two sort of vertical lines, is just going to be 5. Abracadabra, it'll be how many letters is that, right? Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11, I think. So 3 plus 4 plus 4. Yeah, it should be 11, right? So the modulus, the length of the word abracadabra is just 11, right? There's 11 letters that make it up. And that makes sense, right? But obviously, as with anything, right, with sets, you have sort of the empty set. And, you know, as with most things in maths, there is normally something which effectively represents nothing, in a sense. And in this case, it's going to be the empty string. And that would just be a string of length 0. So if I just make another box in here. So if I just make this box in here. Okay. So, and I move this to the, yeah, you guys should be able to see this. Okay, so the next thing I want to talk about is the empty string, which is effectively just, there exists a string with length 0, and we call that string the empty string. So the string of length 0 is called the empty string. And we typically denote it with the symbol epsilon, so written epsilon, and it effectively plays the role of 0, right? In a number system. Effectively, it's a string composed of nothing, so there's not really nothing there, but it still is a tangible thing that we can think about, so we define it in a, what's I going to say, sorry, and it plays the role of 0 in a number system. Okay. Basically, it's a string which is composed of nothing, right? It has no length, so there's no like symbols that make it up, basically. Here, I mean, there's not really much else to it with that, right? Just the same as sort of us having a 0 as like a number, the empty set, things like that. I mean, these things are there for completeness, but also obviously 0 comes up a lot in any maths. 0 probably makes an appearance, right? So, you know, probably these things are also, and I'm not 100% sure about the empty string, but I would assume that also it is used. But I don't know, right? If in any case, definitely it's there for completeness. Okay. So if the length of a string is n, okay, so just some natural number, right? Then or 0 if you don't consider 0 to be a natural number, then effectively we can just write w. Well, we write the string w in this form. So we have sort of the symbols w1, w2, all the way up to wn. So each of those wi's, they're just symbols, okay? And so really we say that wi is an element of some alphabet sigma, right? It's just an arbitrary alphabet, right? So this is just saying that these are symbols, right? This final comment here just says, okay, all of our wi are their symbols. And effectively, you know, as we said before, any string is just basically a sequence of symbols without commas and brackets. So basically that, right? So this is just another way that we write strings in general, like a general way of writing out a string, okay? And obviously, for any string, we can also imagine its reverse. So for example, if I give you a word like car, you can reverse it and get rack, R-A-C, I don't know. And so we actually also define the reverse of a string. So the reverse of w, effectively written as w almost to the power of r, but not really. It's sort of just a superscript, right? So w superscript r is effectively just another string, right? So it's just is the string obtained by writing w in the opposite order, right? Is the string obtained by writing w in the opposite order, right? So i.e. w superscript r is effectively just wn followed by wn minus 1, wn minus 2, all the way down to w2, w1, whereas w obviously we already defined as w1 all the way up to wn, but in this case we're just putting wn first, so we're just like the order of the symbols are basically just flipped, right? So wn starts, then wn minus 1, then wn minus 2, all the way down to w2, then w1, right? So in the case of w superscript r, we're effectively just taking w, which is some string, or yeah, basically just some string, right, or some sequence of symbols without the commas and brackets, and we're just sort of reversing the order. I know that's using the definition in a sense, but basically we're just taking wn, putting it at the front. So the last element becomes the first, second to last becomes the second, third to last becomes the third, and the first element and second element become the last and second to last elements respectively of the string, or symbols of the string. I mean, hopefully that makes sense, right? So for example, if I were to give you this string 01001, the reverse of that would just be 10010, right? This is the reverse of that string. Something abracadabra, the reverse of that is arbadakarba, some word that doesn't even make sense in English, but right, like it's going to be ARB ADA-CARBA, right? So just literally you read the word backwards. And that should make sense because you probably have come across the reverse of certain words before. Like that's natural probably to you. At least it is to me. I don't know. Okay, fine. So, okay, we're actually almost towards the end of what we need to be honest with this. Right, okay. So we also have substrings. So, you know, obviously subsets exist and things like that. So we also define substrings. So we say that a string Z is effectively a substring of W if Z appears consecutively within W. Okay. I mean, I appreciate that slightly informal. But I mean, it's a definition that definitely makes sense, right? Like, for example, if I have the word, abracadabra, abracadabra, then a substring of this word is just any like sort of sequence of symbols within the word, without changing the order of the symbols. Effectively, yeah, that's it pretty much. Any sequence of symbols that appear consecutively within the word, obviously removing the commas and the brackets. So, for example, cad, right? That is a substring of the string abracadabra, or abra, right? That's another example, right? Or dab, right? Like any of those, they're all substrings, right, of this word, and hopefully that makes sense. Like that definition is suffices for now. You see abracadabra. E.g., I should probably say cad is a substring of abracadabra. Cad. Okay. Right. Okay. Now, if the next thing I want to talk about is basically concatenation as well. So obviously you might be familiar with concatenating words. In fact, it's basically exactly what we're talking about here. If x and y are strings, right, such that effectively the length of x is denoted by some natural number or 0m, and the length of y is n, right, then the concatenation of x and y, effectively written xy, is basically just the string obtained by appending y to the end of x. So, I mean, yeah, we can also write it out. So it's not x times y, right, because they're strings. That wouldn't really make sense. It's the string obtained by appending y to the end of x. Right? So, for example, e.g., if x is, written as x1, x2, all the way up to xn, and y is equal to sort of y1 all the way, y2 all the way up to yn, then effectively, in this case, the concatenation xy is just x1, x2 all the way up to xn, followed by y1, y2 all the way up to yn, right? So basically just a string, but we also add on effectively y to the end of x, right? So this all of these are just symbols, right? All the xi's and yi's are all symbols, right, of some alphabet. So we can say that like, we could be specific and say, oh yeah, all the xi's are elements of some alphabet sigma, right? Sigma 1, let's say, and yi is alphabet elements of some alphabet. We already use sigma 1, let's use sigma 3. Yi is an element of some alphabet sigma 4. We could say something like this, but ultimately all we're saying is that we have two strings, right, which you already understand. They're just basically sequences of symbols without commas or brackets, and you just basically put one after the other, right? And so if you wanted to put x after y, you denote that as yx effectively instead of xy, as I've done here. But in this case, we literally just place the string x immediately after y. So like each of these are symbols, and this is effectively the order of your symbols. So the symbol x1 comes first, then x2, all the way up to xn, and then y1 follows, right? So if I wanted to basically, for example, if I have, a common sort of example, using sort of the English language, which is probably where you've seen concatenation before, is, for example, like let's just say that x is the string abracadabra, and y is the string, cad, right? Then xy is going to be the string abracadabra cad, abracadabra. So you keep that string the same, and then to the end you just add on cad, basically, right? So you don't change anything. You're literally just adding cad onto the end of abracadabra. And then obviously yx would be different. It'd be cadabracadabra, basically. Cadabra, right? So they're different, right? But effectively in that case, all we did is we took cad and we placed it at the front of abracadabra, whereas in xy you place it after abracadabra. Okay, so you don't change anything about the two strings themselves. You just basically place one after the other, right? Or place one before the other. I mean, depending on which way that you sort of choose. In this case, just xy or yx. They're two different things, but we can obviously, we need to specify which one we're talking about. Unless they're the same. There are probably some cases, obviously, with words, but you get the same output by appending two different ways. But yeah, I mean, typically, I guess you need to specify which way you're talking about, whether you're appending cad onto the end or at the beginning. But yeah, okay, that should make sense. And just another little piece of notation in terms of concatenation that we have is as follows. Okay, so there's a specific type of notation. So we use the notation effectively x, basically to the power of k, right? But in this context, this basically means x concatenated with itself k times, to mean x concatenated with itself. Don't know why my pen is bugging out here, but that's supposed to say itself k times. So basically, in other words, if you were to write it out, like in the form we've done so far, you just write x, 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 all the way, basically just k x's, right? And obviously x itself is a string, and so basically x can obviously be written as x1, x2, all the way up to xn, and then so therefore you could write x to the k is effectively x1, x2, all the way up to xn, then followed by another x1, x2, all the way up to xn, and then effectively you do this just k times, right? So that's basically just a piece of notation that we have. So in this context, x to the power of k, obviously because x is a string. So if x is a string, then we take x to the power of k to mean this, just concatenating x with itself, k times.
Okay, sorry guys, there's a bit of a gap because I had to leave after filming the last section of the video, so it's currently now the morning of the next day. But we're back, and I'm just here to... There's a couple more things I need to mention in terms of strings and languages. The sort of first thing I want to mention is sort of the lexicographic order of strings. So basically, there's a specific ordering of strings. So just in the same way that you have, like, for example, the ordering on, let's say, integers. So like 4 is less than 5, -2 is less than 4, stuff like that. Just the same as that ordering. You also have sort of a type of ordering called the lexicographic ordering, which is effectively the same as like how you would order, like alphabetical order in a sense, right? Alphabetical order is a lexicographic order, and effectively we extend that to talk about generalized strings, right? Because like words in the English language, they are strings, but they're not the only strings that exist. So for all types of strings, we define the lexicographic order to be the familiar dictionary order. The lexicographic order of strings is the familiar dictionary order. Familiar dictionary order. Right? So for example, let's say that I have an alphabet, let's say sigma 1 from earlier, which is effectively just a set I can get at 0 and 1. Right? In this case, a dictionary order might not be so obvious to you, but basically we can use it to compare terms like this. So first things first, if we have, say, these two strings, right? One of them is just 2 zeros, the other one's 3. Then this one is less, effectively, lexicographically. The second, if you follow the lexicographic ordering, this one here is less than this one. Because effectively what you do is you go each element, so you check, okay, the first element of this one is, the first symbol here is a 0. The first symbol here is also a 0, so, you know, they're the same in that respect. Then you move to this one, and this is a 0, this is also a 0, and now you've reached the end of this string, okay? And so basically you say that this is less than this, right? However, if it was 001, right, then actually this would be greater than 000, because you check each element. So you check the first symbol, okay, they're the same. Second symbol, they're also the same. Third symbol, and 1 has higher priority than 0 because it comes later in the set, effectively. Or at least we assign it higher priority to 0. If I say it comes later in the set, it's not necessarily, because obviously sets, the order can be changed. But we typically assign some priority. And I think it's the way that it's written in terms of like the way that someone writes it in terms of set and the way that they sort of define it is the way that the priority works. In this case, we are assigning priority to 1. Okay, and I've written it as 0, 1 to mean that I'm assigning priority to 1. Obviously, that's the same set as the second elements 1 and 0, but I'm writing it in a specific way to sort of say that I'm assigning priority to the 1. And so in this case, 001 is lexicographically sort of greater than 000 because I compare each element, right? So I compare the first symbol of the first string to the first symbol of the second string, and I keep moving until either I have the last scenario where, for example, I finish one string and I haven't found anything that's different, so the shortest string will prevail, it will be less than the longest string, or until one of the symbols is different, right? So in this case, we reach the 1, and that obviously has higher priority than the 0, so that means that 001 is greater than 000. In the same sense, the alphabetical order that you're familiar with is just basically this, but just with like a different alphabet. So obviously it's just the alphabet in this case, it's just literally the English alphabet, for example. And in this case, Z is assigned the highest priority. So if I were to arrange these words in alphabetical order, right? So let's say I have like cat and, you know, tab, for example. Well, first thing I do is I check these, and I realize that T has higher priority than C. So cat is going to be less than tab in terms of alphabetical. Like if I were to order words alphabetically, the word cat would come before the word tap, right? And you know, if I had another word, I'm trying to think. If I have a word, let's say car, for example, right? Then obviously these two are the same, okay? So that's fine. This A is also the same as this. So then I come to check the last one. Let me see if it's going to be QRST. So R comes before T. Okay, so this one is actually going to be less than this one. So CAT is going to be greater than CAR because that's going to come later on in the alphabetical order, right? And T is high priority because it comes later in our alphabet, at least in the way that we've written it here. Okay, so whenever, I'm pretty sure whenever you write it in this form, you're assigning priority based on the way that you've written it, even though the set can be written in other ways. It really... Then also from context, they should tell you, or it should be clear which elements have priority when you're talking about lexicographic order. But that's pretty much all it is. It is just literally the familiar dictionary order. Like you're literally just giving elements priority, and then you're just searching one element at a time to find a difference. And then when you find a difference, the high priority takes over. If you don't find a difference, then the shortest string is less than lexicographically the longest string. Okay, basically that's that. Okay. Fine. So there's a lexicographic order. There's also a modified lexicographic order called short lex order, which is sort of similar in many senses. So a modified lexicographic order called effectively short lex order or string order. Effectively, they're the same. Short lex order or string order is in many ways identical to lexicographic order. So it's identical to lexicographic order, except basically all shorter strings, all strings that are shorter will come before all strings that are longer. And I'll explain exactly what I mean. It's effectively identical to lexicographic order. Right? Except that shorter strings precede longer strings. So they come before longer strings, basically. So for example, in this sort of ordering, in this short lex ordering, the way that we might, for example, order, let's say that we have our alphabet from 4, let's now call it sigma subscript 2, and it's just the set containing element 0 and 1. In this case, some sort of short lex order on this alphabet effectively might be something, will look something like this, right? So effectively, will effectively be like this. So you'll have epsilon first, right? Because that's like nothing, right? That's basically the 0 string. Then you'll follow that with 0, right? Because 0 has lower priority than 1. And then you'll have 1, right? Because 1 is high priority. Then you'll have 0, 0, and then 0, 1, and then 1, 0, and then 1, 1. And then you start the strings of length 3. So then you'll have 0, 0, 0. Then you'll have 0, 0, 1. Then you'll have, 0, 1, 0, and things like that, right? And so effectively, in this case, with this specific ordering, the length of the strings sort of is more important than necessarily what take priority. Because before you might say something like, oh yeah, the string 0, 0, 1 is clearly less than the string 1, 0, because if I compare the first elements, oh yeah, 0 has lower priority, so immediately I can say that this is less in a lexicographic order than what the string 1, 0. But in a short lex order, that's not true. In fact, 1, 0 is going to be less than 0, 0, 1 in that order because it has a shorter length. So in that order, it's actually easier for us to be able to discern, right? Because you can just see this is a shorter length, so immediately it's less. But it's just sort of like a modified lexicographic order that we use, and you can see how it's working in this case. Okay, so yeah, this is basically just the short lex ordering of all strings over the alphabet that we're considering. Okay, last couple of things now that I want to talk about is effectively, one of the things I want to talk about to finish off with is sort of the prefix of a string. Okay, so we say that, string x, effectively, so a string x, so we just defining x to be some string, right, is a prefix of string y, right? If, okay, so x and y are both strings, okay, effectively just sequences of symbols without commas or brackets, right? So we say that string x is a prefix of string y. If, there is a string z, so if a string z exists where, well, really such that xz is equal to y. So when you concatenate x with z, you just get the string y. So you can think about x and z as sort of components of y, in a sense, right? And x is the prefix because it's the first component, right? So x comes at the front, and then so there's x, and there's just a bunch of other stuff, and that makes up y, right? Because remember, this concatenation stuff here means that if x is basically a string, it can be written in this form, right, of length. Let's say it has length n, okay, and z has length m, so let's say it's written sort of, sorry, not x, z1, z2, all the way up to zm. Then when you concatenate them, you're just basically, at least writing out xz, you're placing this at the end of sort of the string above. So that's just literally being placed on the end of the string above. And so effectively we're saying that this is going to give you y, right? And I just literally put the symbols directly next, all the symbols of z in the same order directly after all the symbols of x, right? That's just concatenation, right? And that should be fairly, hopefully you get that concept by now. And if not, I would definitely think about it because it's definitely an important concept. And so basically now, once you plug all the entirety of z, right, in the same order after the entirety of x, you just get y. And then we say that x is effectively the prefix, because it's all the stuff that happens at the beginning of that string, right? Because we're saying this x stuff, this x string is at the very beginning of y. Then there's a bunch of stuff after it which we don't really necessarily, well, we do care about it because obviously we assign it a separate string. There's just a bunch of stuff afterwards, right? So x is our prefix string, and then z is effectively just all the stuff that happens after. And combined, they make the string y. Okay, so once you concatenate them together, you will just get y out of it, right? Okay, hopefully that makes sense. It's very similar. I mean, this is very similar. You can literally use the English language to pretty much understand most of this. Like obviously in English we have certain prefixes of words and things like that as well. It's literally the same because words are literally just strings mathematically. So we're basically taking those kind of ideas and then just moving them into sort of maths in a sense, which is pretty cool. Okay. We also have a notion of a proper prefix. Okay, so x. So a string x is a proper prefix of y if it is a prefix of y. So that's the first condition. if it is a prefix of y, right? And you know that we need to also have a condition that x is not equal to y, right? Because obviously it being a prefix means that xz equals y for some string z, right? Obviously they're all strings, x, z, and y are strings. But we could legitimately have z just being epsilon, so we could just have z being the 0 string, in which case actually x is equal to y, right? Because effectively you're just appending nothing onto x. Because if z has no symbols composing it, then you're just concatenating x with nothing, so you're just going to get x back, and you're saying that that is y. So x is the string x will be effectively the same as the string y in that specific case. So we say that a proper prefix is basically just not every single case where we have a prefix except for that one. So basically, this just means that z is not equal to epsilon, right? That's pretty much what we're saying. Right, and to finish off, we have this concept of a language, okay? So a language, which is really, you know, this entire title of this thing is called strings and languages, but you kind of need all of this. Well, you don't really necessarily need all of this. You don't really need the prefix stuff to talk about it, but I guess you didn't necessarily need like lexicographic order, that stuff. But it's kind of like the endpoint in a sense of all of this. Effectively, language is basically just a big set of strings, okay? So a language is a set of strings. Okay, that's pretty much all it is. So, you know, if I give you an alphabet, it doesn't necessarily need to be this set of all possible strings in that alphabet. It could just be, you know, some subset of strings. So, for example, let's say that I give you the alphabet, you know, sigma 1 is equal to, you know, just the English language, right? So just all the letters in the English language, or the symbols effectively in the English language, right? That's terminology. But then obviously there are many words that you could make from these letters that aren't really words in the English language, right? Like for example, maybe it could be like this, right? Like that is a string I can make. Sorry, I should be more specific. The string I can make, that's not really a word in the English language. So it's not really a member of the language, but it's still a valid string. Okay, so the language doesn't necessarily need to be a set of all possible strings that you can make from a specific language, just a subset of those, effectively. So just some set of strings. That's it. It doesn't specify, and that's why it doesn't specify like the set of all possible strings from a language. Doesn't from an alphabet. Sorry, it doesn't need to be. I've been saying language instead of alphabet. I think I meant alphabet. Hopefully, I haven't saying that. But effectively, yeah, it's not a set of all possible strings that can be formed from an alphabet. It's really just a set of strings from an alphabet, like, and whatever that set is, up to you, right? And like, so the English language is obviously an example of a language because it's effectively just a set of strings from this specific alphabet. Yeah. Or over this specific alphabet, I guess. Okay, fine. And we also have this final thing here, which I guess we did kind of the prefix stuff to talk about this, but there's no immediate use for this. But it'll probably come up later, I assume. That's probably why they're mentioning it. So a language, so we say that a language is effectively prefix free if no member is a proper prefix of another member. No member is a proper prefix of another member. I'm trying to think of an example in the English language. So yeah, an example that sort of comes to mind is, for example, super. So like the string super is actually a word in the English language, right? So if you're, you know, you're super, like you're like almost like a superhero, except that super is basically the prefix of that string superhero. But like super by itself, I guess does make sense as a word, or I believe it does anyway. Probably should specify that super. You know. Yeah, like, you know, you're saying it's like this thing was very good, right? Like basically that's what you're saying. You're saying, yeah, this is an example. Julie was a super girl, that kind of thing, right? So like it means very good, effectively. So it's a word by itself, but also it's a prefix, right? So this is a word in the English language. There's a word in the language that is effectively English, and then you can just add like hero after it, and that becomes sort of a new word. So actually, if we were to take the English language, a specific example of a language, then it wouldn't necessarily be what we could say prefix free, because no member, effectively there exists a member that is a proper prefix of another member, basically. So it wouldn't be a prefix free language. Obviously, in terms of like maths, the English language is the only language out there that exists, right? And we can take this much beyond that. But I'm just using that as examples because it's very simple to sort of associate for a lot of people the English language, because maybe they've used it quite a bit and they're sort of slightly familiar with it. But you know, this obviously extends far beyond just the English language. We're talking about languages in general. But effectively, the English language is not a prefix-free language because the word super is effectively a string in that language, and superhero is another string in that language. So super is obviously a proper prefix of superhero because the two strings are not the same. And you can write effectively superhero as super and then hero. So hero there would be your Z, and super would be your X, the string X from the sort of XZ equals Y that we have up here. But yeah, I mean, that's pretty much it, right? There's really not much else to talk about here, actually. So, yeah, that's that, guys. Thank you very much for watching. This has been Strings and Languages. Pretty short video comparatively, I think, to some of the other ones. So yeah, nice. Thank you guys for watching. See you guys in the next one.